We're in lesson 19, solving exponential equations, and we're looking at page 259, problem number 11. And here's what we know. The growth of a population of E. coli bacteria can be modeled by the function e of t equals 500 times 11.547 to the t power. And the growth of a population of Salmonella bacteria can be modeled by the function s of t equals 4,000 times 3.668 to the t power. And effectively, just to kind of translate this for us, that means E. coli, when we first started tracking the population, it started at 500 and it's growing by 11.547 times each hour. So after the first hour, 500 times 11.547. After the second hour, times 11.547 times as well. It's getting 11 and a half times as big from its starting population of 500 every hour. Whereas Salmonella started with more bacteria, 4,000 cases of it, or 4,000 bacteria, and it's growing at a rate of 3.668 times per hour. So it started at 4,000 and then went up 3.668 times after the first hour. That product times 3.668 for the second hour, and so on and so on and so on. And we want to use the property of logarithms to find t when they're the same. So effectively, here's what we're really doing, is we are going to take the E. coli's exponential growth situation starting at 500 and growing by 11.547 times per hour, and Salmonella's exponential growth population where it started at 4,000 and grew at 3.668 times an hour, and we're going to set them equal to each other. So let's do that. All right, 500 when E. coli's growth equation, how we can model it is set equal to cool. And again, all that we're doing when we set them equal to each other is literally doing as it sounds. We're taking the two functions, the two growth models, and we are setting them equal to each other. Cool. So now what we want to do right off the bat is we want to use logarithms to our advantage. So we can use logarithms to our advantage by logging both sides. And one thing that we can do here is use a common log to help us out and do so. Although actually I overlooked something, and that's that we can get rid of one of these starting values by dividing. Effectively, what I'm talking about is since we are dividing by t, we're trying to find t and t is an exponent, we're going to be using logarithms. But I could divide both sides by 500 right off the bat, because when I do so, it makes one side of my equation a little bit more easily seen, and that is going to be the right side, where now we just have 11.547 to the t power is equal to the quotient of 4,500, which is going to be 8 times 3.668 to the t power. So I started to talk about common log, but I almost overlooked a little bit easier operation, that's division, to make this a more palatable equation. Now what I can do is I can log both sides. And I'll do this here in purple. I'm going to log the left side. If I log the left side, I have to also maintain property of equality and log the right side. So let me move it out a little bit. And now what I'm going to do is I'm going to actually execute properties of logarithms, and I'm going to execute two of them. One properties of logarithms is going to be the power property, and the other is going to be the, let me use a different color here, product property. So power property is going to be done on both. And I'll show you where here on orange, boom, and boom. And the reason why we can do so is because we have arguments raised to a power. And what the power property of logarithms tells us that we could do is that we could take an entire logarithm and instead of raising it to the t power, we could multiply it by t, bring it on down effectively is the way we've been kind of discussing it. Bring that on down. Power property, awesome. And we can do the same thing over here on the right, but before I do so, I want to use the product properties, because right here, I am actually finding the product of these arguments, 8 and 3.668. So effectively, what I'm going to do is I'm going to turn this into log of 8. Bear with me as I copy and paste here. Times log of 3.668 to the 8, but the product property states that when you are multiplying arguments, you turn to an addition of the two logarithms. So now we have a log of 3.668 to the t. So the product property allowed me to work this entire situation being highlighted in blue and turn it into an addition of the logs of the two arguments, 8 and 3.6 to the t. Now I can leverage my power property one more time. And again, I can have right here, bring my t down in front. So we can room here and bring that t on down in front. Boom. My power product property is done. And now what I've done is turned it into a very difficult looking equation, but an equation where now our exponents or our unknowns aren't in the exponential form. So now I can kind of work to manipulate this problem a little bit easier. So I'm going to, unfortunately, due to the lack of space, I'm going to have to bring this on down here. And what I'm going to do right off the bat is I'm going to subtract. So I'm going to subtract this t times log of 3.668 from both sides, which will now, as I move it on down, turn this into a little bit more easily seen problem here, where I still have my left side t times log of 11.547. And again, now I'm subtracting this whole thing here from both sides. And the reason why I'm doing so is to effectively get every single thing that has a t on the left side of my equation. And since I subtracted this from here, it's now gone, leaving me with just log of 8. Copy and paste that again, because that's all I have left now on the right side of this equation. Cool. So at this point, I have a bunch of t log there. I'm going to use GCF. I'm going to factor out a common factor from both these situations, and that hey, both of these have a t in it. So I'm going to remove that t. And then I have a factored form where the GCF of t is gone. Boom. So I got rid of the t in both situations. A little bit of a tricky move there, but I saw that they both have a t in common, so I factored it out. And now I can actually get closer and closer and closer to solving for t, because notice t is just being multiplied by this humongous, and we kind of slow it down here, t itself is just being multiplied by this humongous parenthesis, this huge thing being highlighted in purple. So really all I have to do to isolate t is divide by that. So now final step is I'm going to divide both sides of this equation by this logarithm subtraction problem. Because keeping in mind, despite the fact that it looks intense, this humongous logarithm that's now in our denominator is really just a number, and it will be a number when I evaluate it with the calculator. So this is all gone now, leaving us with just a t. Sorry I have all this writing. They didn't really give us a lot of space here to do this pretty monstrous problem. But now really all I have left after doing all those moves is just a t, and it's isolated, and it's equal to whatever this quotient is on the right side. You know what that means? That right there is pure calculator time. So let's go to our calculator. Let's call this out. And let's type in what we knew. We had a log of 8 in our numerator. And that will be divided by what we had was a log of 11.547 minus log of 3.668. And now we have our solution here. 1.8133 rounded to the 4th decimal place. Again, when I evaluated this whole thing in the calculator, I got 1.8133. So therefore it takes, we'll call approximately 1.81 hours for the population of Salmonella and E. coli, given these situations and growth rates, to be the same size.